Well, good evening everyone. So welcome to the day 5, which is to be on Friday. So this question is for 6 marks and this solution will be published on Friday evening 5 p.m. Okay. So this question is about a probe in orbit. So it is about a circular motion. So the question is for 7 marks. So I have taken 7 minutes to solve this. A probe of mass m is in a circular orbit of radius r around a spherical planet of mass m. Okay, so there is a planet and there is a probe which is now moving with a velocity v. State why the work done by the gravitational force during one full revolution of the probe is 0. What is the reason? Because we had seen this in the classroom also. So the force, what is the force over here? The gravitational force R, which provides a centripetal force. This F is perpendicular to the velocity direction, right? Velocity, and we know that the direction of velocity is equal to the direction of displacement, which means what? So this displacement direction, this are both on the same. So as a result of it, the work done by the gravitational force given by F dot S, which is equal to Fs cos theta, right? Now what is the value of theta here? This angle over here. What is the value? Theta is equal to 90 degree. Whatever could be the value of F, whatever could be the value of S, but still this theta becomes 90 and hence this becomes 0 because cos 90 is 0. Okay, so therefore even if I write this as F into S over here, so Fs cos 90 should be equal to 0. So thus this is equal to 0. This is what you need to write. Okay, and then deduce for the probe in the orbit that its speed is v equal to root of gm by r. So what is happening? You have the, what is that you have? You have the planet over here, and then you have the planet over here, and then you have a satellite or a probe which was moving like this over here in a circular path like this, right? So this was the radius r. So my circle is not so good, but anyway, consider this as a circle. Okay, so as a result of it, we need to prove this one here. So how do we prove? We know that if v is the speed of the satellite, okay, and if a particle is moving in a circular motion, what do we know? We know that the centripetal force mv square by r should be equal to the driving force. Now, what is driving it? The driving force is nothing but the gravitational force. So I will write mv square by r. I have written capital R, I have written small r here. Okay, note the change over here. Actually, this is the formula, but you can replace it because in the problem it's small r. So I am replacing like this: mv square by r is equal to gm. This is capital M, this is small m. gmm divided by r square. This m and this m goes away. So you get this r square and this r goes away. So v is equal to square root of gm by r. Okay, so thus we have got this. So just writing like this will not fetch you the mark, but you need to label it appropriately. Okay, you can say if m is the mass of the planet and small m is the mass of the probe, then what do you have? Then probe, then what do we have? We have mv square by r. You write this equation. Okay, and finally arrive at it. Right, now let us move on to the next one here. Total energy E is equal to minus GMm divided by 2R. This is what we need to prove. Now, what is total energy given by? Total energy is given by potential energy plus kinetic energy, right? What is potential energy? Potential energy for a planet and a satellite. How is this given? This is given by minus GMm divided by R. Okay, so this is your potential energy. And what is kinetic energy? Half mv square. Now we already proven that v is equal to root of gm by r in the previous expression. So I will write this as minus gmm by r plus half m into a gm by r. Now let me simplify this. So this will now become minus gmm by r plus gmm divided by 2r, which will now become minus gmm divided by 2r. Okay, as required. See, what is the question? The question is prove that it is equal to minus gmm by 2r. We have proved this here. Now let us look at the next one. So C part, it is now required to place the probe in another circular orbit further away from the planet. Okay, now before that, let me look at how is the mark is getting distributed. One mark goes for here, the other mark goes for the final answer. But don't just stop here, you need to show the full working here. Okay, let us go on for the next one. It is now required to place the probe in another circular orbit bit further away from the planet. To do this, probe's engine will be fired for a very short time. So this is the planet once again. So this is the actual probe which is revolving in this circular orbit of radius r. Now what you want to do? You want to keep it further away from the planet. Maybe I want to put it here. I want to put it over here in this new orbit. So probe's engine will be fired for a very short time. State and explain whether the work done on the probe by the engines is positive, negative or zero. State whether the work done is positive, negative or zero. This is the question. So how do we now see? There is no mathematics required here to show anything. Okay, so what you need to do is you should say, okay, so let us say potential energy, total, what's the total energy here? Total energy here should be equal to minus GMm by 2r. If I consider this, let us say this is your R2 and this is your R1, right? This is your R1, this is your R2. So here what will be the case? The total energy would be minus GMm divided by 2R2 here. Now total work done. So what is happening here is that, see, R2 is greater than R1, which implies 1 by R2 is less than 1 by R1, right? When I say 1 by R2 is less than 1 by R1, which means what happens? This, if I multiply this by GMm on both the sides, what do I get? GMm by R2 will be less than GMm by R1. Okay, but there is a negative here. If I multiply this by minus also, then I get minus GMm by R2 is greater than minus GMm by R1, right? So therefore, now you see what happens here. So this energy is higher, right? This energy is higher. So if this energy is higher, that means you need to supply a large amount of energy for it to go. In other words, the work done should be greater than zero. You should do more work to make this particle, to make this orbit to go from here to here. So mathematically you can state like this. Logically you want to state, what you can say is, you can say the gravitational pull is more here and lesser here. So in order to make the object move from one orbit to another orbit, you need to do some work. So this work done is positive. You can argue it like that also. Okay, now let us move on to the next one. I already crossed the limit. Okay, we have finished it now totally, right? Okay, thank you. Let us see some more problems in the next week.